examples. Huh? So let me try to write it on the PPT. Just opening a new blank PPT. I'll send you all these PPTs to you by mail. Just it's opening. Huh? Just 1 minute. Huh? Let me share the Can you see the screen? Hello, can you see the screen? Empty screen?
Yes, sir.
Okay. So we were looking at these LP spaces. What I wanted to give you is we have not done any examples. So it's good to look into some examples here. As soon as we see the LP spaces, so this is the Let me erase this. So let us recall. You have LP spaces. Let me look at R first. One less than or equal to P less than infinity, and even infinity also. So we showed in the last time that these are all Banach spaces. Okay. So let us look into some examples. Let's take P equal to 1. So these are all sequences X in S such that summation mod Xi is finite. I equal to 1 to infinity. See, this is also can be written as summation mod Xn n equal to 1 to infinity. Okay, this one. This also can be written as Xm. So this In are dummy suffixes, or can be L or anything. Okay. So the first thing that you should perhaps know is what are the elements which does not belong to this one. So you can take the sequence 1 half, 1/3, etc. 1 by n. Dot dot dot. This is not in L1. That is because summation I equal to 1 to infinity 1 by n is actually infinite. You know this or not? Huh? You know the proof of this? Hmm? So I hope you know the proof. If you don't know, I will do it in the September. Or if you want, I can do it now. Do you know the proof or not? Okay, let me ask a different question. Do you want the proof or not? And I am telling you about summation 1 by n is infinity. Do you want the proof or you know the proof? Quickly answer. Huh?
We know, sir.
Okay. What about summation 1 over n raised to p 1 less than p less than infinity? Is this finite or infinite? This is finite, right? The crazy book on series for the proof. So this is finite. Now, for example, you want to construct some example in say L2. Okay. So suppose you want to construct an example in L2R using this. Okay. Now, if you look at the sequence an equal to 1 by n equal to 1 to 3. So that is the sequence A equal to an. This an, this A is not in L1. But when you look at the summation mod an square, this is actually summation 1 by n squared. This is finite by this theorem. Okay, so that shows that A is not in L1, but it is in L2. Okay, this is one thing that you should understand. Now, what I am trying to tell you is this LP contained in LQ, LQ contained in LP. This you have to be clear. Okay, if it is true, give a proof. If it is not true, give a counterexample. Okay, now obviously L1 is not in L2. Okay, rather, what is that we showed here? We showed that A is not in L1, but it is in L2. What does it give you? It gives you an idea that there is an element which is in L2 but not in L1. Okay, so that means L2 should be contained in L1, right? So that we can think of it. So you think about this. So think about it. So how do you construct it? Suppose you take P and Q. Okay, take two numbers P and Q. One less than P, less than or equal to infinity. Okay. Let's assume this P is less than Q. So let us write say P equal to P plus delta, delta positive. So you look at this sequence, right? 1 by n. Raise it to appropriate power, right? Appropriate power so that it is in one space LP but not in LQ, or not is in LQ but not in LP. So this power K, you choose it. How do you choose that? Now, for example, if you take K equal to P, take K equal to B, and if you look at this B equal to, not B, summation 1 over n raised to P, since P is greater than 1, this will be convergent. Okay. So this series, so if you take this sequence 1 raised 1 over n by P, it is in L1. Right? If you slightly reduce this P, summation 1 over n raised to say P minus half, right? Something close to it, okay? Then this will not be in, this may not be in LP, okay? Because this is in, let me not say that. You choose in such a way, okay, let me choose, let me give you, let us take half equal to P plus Q, okay? P plus Q or P minus Q. So I want, given P, I want P plus Q to be half. So how should I choose P? So it should be P plus half minus P. Then this will cancel. Right? You get half equal to half. So given P, choose Q equal to P minus half. Then if you look at the summation, 1 over n raised to Q, this will be n raised to, say, P minus Q or something. Okay? P minus Q. Then this will be actually half. Summation 1 over n raised to half. This is not convergent. So for this index, P minus Q, which is half, given P, it will not be in LP. This is how you construct examples. Okay. Let us take one more comment. Let us take L2 of R and look at the sphere of radius 1 in L2. What is this? This is set of all x in L2. Let me take R2, okay? It's set of all x in so let me take L22, okay? L22 means set of all ordered pairs such that mod x squared plus mod y squared is 5. Euclid is there. So you take this 2 meant for 2 coordinates, okay? You can do this for L and R. So this is the sphere of radius 1. How does it look like? It looks like a disk, right? This is the. Let us look at L1 to R. I want to draw B01 in L1. L1 to R. What is L1 to R? It is mod x plus mod y pi. That is with L1 R. So how does this B10 look like? It is set of all xy such that mod x plus mod y. So let me write it first for the sphere of radius 1. That is mod x plus mod y equal to 1. This is the circle. Okay. I want to draw the graph of this. Okay. So how do I draw the graph of this mod x plus mod y equal to 1? And then we'll come to mod x plus mod y less than or equal to 1. Okay. So there are 3 cases here. So you have to draw the graph in 2 coordinates, right? So this is the first quadrant. This is the second quadrant, third quadrant, fourth quadrant. So we draw the graph in this. Now let us take the first quadrant. Okay. In this case, x is positive and y is positive. Right? So what you have is mod x equal to x, mod y equal to y. So what you get is x plus y equal to 1. This one will reduce to x plus y equal to 1. What is x plus y equal to 1? What is this? It's a straight line. How does it look like? When y is 0, you have x to be 1. When x is 0, y to be 1. So what is the straight line? This is the first line that you have. Similarly, you have the second line here. Okay. Then you have the third line here. And the fourth line. What is this figure? Yeah. Tell me, what is this figure? Rhombus, right?
Yes,
Or no?
sir.
So the sphere in L1 to R is a rhombus. It is not, although we call it as a ball, actually it's not a ball. Okay, that's what I wanted to tell you. This was one of the assignment problems that you had. Unfortunately, we are not meeting for solving the assignment problem. That is why I'm using this lecture for solving the assignment problem. Okay. So this is so similarly, let us take the third example. What is the third example? Let's draw the figure in L infinity 2. What is this? This is set of all xy such that mod x mod y is bounded. That's obvious, okay? Because it's only 2. So let us draw the graph. Say d1 0 in this L infinity to R. Okay. So how does this look like? So you have to draw the graph of, okay. So you have to draw the graph of this L infinity norm. Let us write first the graph for this. Okay. What is this one? This is supremum of mod x mod y. That is the maximum or supremum equal to 1. Okay. As usual, let us take the what do you think this supremum means? Huh? Let us take x equal to 0. What is supremum of mod y equal to 1? So when I take x equal to 0, I'm here. So mod y will be equal to 1 because this is 0. So since we are in the first quadrant, it will be just this line. Right? So when y is 0, what you get is x equal to 1. X equal to 1 is this line. Similarly, you complete this, you will get like this. Okay, this is minus 1. This is plus 1. Okay, this is 1. This is minus 1. So this will be the figure, including this, which will be supremum of mod x comma mod y less than or equal to 1. This is the boundary. Okay. That's what I wanted to tell you about the, okay. The next gap, fourth, the gap. Okay. Set is open. So let's take some nonlinear space. Well, let me call it a E with an R. So you take a set A in E. It is called open if and only if for all x in A, there is a ball of epsilon radius around x contained in A, right? This is the definition of open set in metric space. So let us look at this. Okay. So this example here is again L2. Let me take 2. Usual Euclidean plane. So this is the Euclidean plane. Now let me take this set A equal to R. How does this look like? So this set A will be, okay, set of all x comma 0 in this L2R. Okay. That's an element here. This is this. Is it an open set or a closed set? So take a point. So let's take a point here, the x. If this has to be open, then I should find out a open sphere around this point contained in this line. Is it possible? Can you have a disk inside a line? Yes or no? See, this is one dimensional. No, this is the disk is a 2 dimension. How can a 2 dimensional stuff sit in 1 dimension? You can't have a disk sitting in R. Clear or not? Therefore, this set is not open. Okay. See, that is what happens in one of the examples that we have. Okay. What is that? The exercise, one of the exercise. So what is that exercise that you have? One minute. This is the gap P. You have X to be a non-linear space. Y not equal to X is a subspace. Then what we said is this interior of Y is empty. This is one of the questions in your thing. So what is this? So if you have A in X, what is this interior of A? Interior of A is defined to be A with a 0 on the top. This is nothing but the definition is set of all interior points. Okay. What is an interior point of A? So X belonging to A is called an interior point. if and only if there exists a ball of radius epsilon around x such that this ball of epsilon radius x is contained. You know this or not? You know this definition?
Yes, sir.
Now, what does this y interior equal to empty? It says that if you have a subspace which is proper, then its interior is empty. Okay. So what I was trying to tell you is that if you have a subspace, its interior has to be empty. The same proof what we gave for that the real line is a subspace of R2, but although it's a subspace, but its interior is empty. Okay. So it's about 53, 54. Hey, what happened to other students? Huh? There are only 6 here. They have class or something? Sonu. Hello?
No, sir, I don't know, sir. I think they have not joined, sir. There is something drone show going on, I think.
Huh?
I don't know, sir.
What?
I don't know, sir. Something like some kind of show, drone show, maybe Indian IT or admin, maybe.
Then they need not have put a class, no?
Yes, sir.
See,
I don't know, sir.
what I am doing is
I will talk to them, sir.
These are the sort of questions that you are asked in an MSc interview or a PhD interview.
Yes, sir.
That is why I am doing more examples now, because these examples may not be given in books. All right, let us. Any questions? Anybody else has to ask? Anybody has any questions to ask?
No, sir.
Sure. Are you happy or unhappy? Feel free, huh? Today there was some problem with the internet. It's very unstable here today. Okay, then I will stop the class. It's 54, 1 minute before. Have a good day. Bye.
Bye, sir. Thank you, sir.
Bye.